Now let's look at the case with 3 data points. Is there a line that passes through all 3 points? No. Unless the points are perfectly collinear, it's impossible for one line to pass through all 3. So, as you can see in the animation, the sum of all the squared errors cannot be 0. The same goes for 4, 5, or more points. Now we want to draw the line that minimizes the errors. Unlike before, the loss function L is not 0. So to draw this red line, we need to find the values of W0 and W1 that minimize the errors using a different principle. What principle is that? Let's see. The loss function L is the sum of 3 squared terms, and none of these terms can be guaranteed to be 0 because the points are not on the same line. We can write this more generally. We sum the squared errors for all 3 points. This should look familiar. It's exactly the SSE formula. And if we divide by the number of data points, we get MSE. Now let's plot the loss function L with respect to W. Does the shape look as expected? In reality, the original data can produce a very extreme shape, but I normalized the data to make a nice, understandable bowl shape. The red point on the graph represents the coordinates of W0 and W1 that minimize the MSE. The L value at that point is the minimum MSE. And with these values of W0 and W1, we can construct a line that best fits the data. We can also see that the MSE function, expressed in terms of W0 and W1, is convex, just like a simple one-variable quadratic function. What does this mean? By taking partial derivatives with respect to W0 and W1 and setting them to 0, we find the slope and intercept of the line that minimizes the MSE.